Hello back, my dear students. This is now the last part number 3 with our energy band diagram lecture. Lecture number 3 is the solid state course. In the first two parts of the lecture, we deal with the energy band diagram under what's called the thermodynamic equilibrium, where there is no electrical field applied. And maybe in the second part of the lecture, we examine the case when we apply a potential, if you remember. And we also study how this will affect the energy band diagram in a form of a tilting. However, such a tilting may be due to an applied external force or applied external electrical field, or what's called an internal effect, like this example, where the semiconductor device is still under thermodynamic equilibrium. However, some internal electrical field or internal potential, or what we call later on in the next lecture, what we will call it the built-in potential that can appear in different devices. Now, in this lecture, we are going to study what are the reasons according to where we can have an electrical current. Why should we have an electrical current? Under which condition we will have an electrical current? Okay, so in order to study this, we should always keep attention to the general definition of the current. The current is a rate of change of free carriers. I believe that now you can understand this equation clearly. Carriers are electrons in the conduction band, free electrons in the conduction band, or holes in the valency band. Free, so that we limit our electron definition to the conduction band and our hole to the valency band. Moving, then we have an external source that drift the electrical or the carriers. Like, for example, what happens here when you apply this potential to electrons starts to drift toward right and the hole starts to drift toward left. So these are the three main purposes: carriers, free, moving. Then moving free carriers will cause current. So in order to have an electrical current, you should have free carrier, and this carrier should transport, should move inside the material. How carrier will move inside the material? Now let's start with our basic example with this energy band diagram, including the valency band, the conduction band, the valency band, and the intrinsic formula. Whenever we have a thermal energy, then we have a free carrier. Usually I stop and ask you, do we have current in this stage? Do we have current? The answer typically is no. We have a free carriers, but these free carriers are not moving in a guided way. They maybe have what's called a random walk due to the thermal energy. However, no guided motion occurs. But what if you connect this material into a potential source? Now, this is a source where you can have a guided motion. A tilting will start to occur. So electrons will drift from the left-hand side to the right-hand side, seeking for a minimum potential to apply what we call the minimum potential theory. So the potential here is higher than the potential there, so electron will drift toward the lower potential going into the positive terminal. On the other hand, holes will move to its lower potential again, because as we mentioned, the higher the energy whenever we goes downward for the hole. So the lower potential from the hole perspective is this side, which is the left-hand side. Accordingly, we have a current. So the first reason to have a current is simply to have this potential source, to have this electrical field. And based on that, we have already concluded half of this equation, if you remember from chapter 2, when we say that this J current is equals to, or maybe in chapter 1, I'm sorry, this current density is equal to N, where the N is the electron in the valency band, times the Q, where the Q is the charge, times the Vd, or times the drift velocity, and I'm now associating this Vd with a subscript E to indicate that this is the drift velocity due to electron. By analogy, we can write a similar equation to describe the holes, saying that J also equals to P, which is number of holes, plus Q, charge, plus VDH, or the drift velocity due to holes. Now, the current is a summation of two components. The first component is the current due to the electron, and the second component is the current due to holes. We can rewrite this equation, if you remember, my dear students, the term mu, or the mobility. So we can say that J equals NQ mu eta, PQ mu eta. Here we have the term mu N and the term mu P. If you remember the mu, which is the mobility, one of my interesting exam question is to compare between these two terms. If you remember, this mu term is a function, is inversely proportional to the effective mass. So mu n is inversely proportional to the effective mass of electron, and mu p is inversely proportional to the effective mass of hole, and that's why the current due to electrons is larger than the current due to hole, because simply mu n is greater than mu p. Those students who are attending the extra classes maybe already recognize this fact. So this is the total expression expressing the current due to the electrical field. As you can see from this equation, that the main purpose of having J is the existence of eta. This eta of the electrical field is simply this battery, this potential source. So simply, if you turn off this battery, if this eta tends to zero, this current will automatically tend to zero. So based on that, here, of course, this is the relation for the effective mass. I just mentioned it later, a few seconds ago. So as you can see here, the mobility is inversely proportional to the effective mass for both electrons and holes. And as you can see here, what we can make is just we can get eta as the common factor, and now we can define all these terms as sigma. Again, this is a new version of our Ohm's law. If you remember, in chapter 1, we drew the same equation, but with only considering the electron. Now we are considering both electrons and holes, and we get a general term for sigma as NQ mu n plus PQ mu p. Now let's go more towards sigma. What about sigma? So as you can see, sigma depends on N and B. We already investigated a lot of time, maybe in chapter 2, in determining N and B, either in the intrinsic case or under N-type doping or a P-type doping. So we already can calculate N and B. Mu N and mu B, or the mobility of the electron and mobility of holes, are a constant for a given material for a given temperature. And of course, Q is the unit charge, which is 1.6 times 10 to the negative 19. So simply, you can write a general equation for sigma in this manner. And maybe you can also have what we can call a simplified version of sigma. I mean, if you have an N-type material, for example, whenever you have an N-type material, then, if you remember your chapter 2 well, N will be much greater than P. So you can easily eliminate this term, and so you can say that sigma is approximately equal to NQ mu n. This is simply because now N is much greater than P, which is the sign for N-type material. However, when the material is a P-type, then you can say simply that we can ignore this N in term, and then sigma is equal to PQ mu n, which is a very logic equation. So this is generally the main source, or the first source of current, is to have this electrical field, which is due to this battery. You remember, this electrical field is simply volt over meter, but we already have learned in the first and second part of this lecture. So now, due to this eta, you have a current, which is simply Ohm's law. V equals I for R, J equals sigma eta. Very simple. But what is interesting now, that this is not the only source of current. We may have current due to another reason, not only electrical current. What is the second source to have an electrical current? Let's see into this. In order to describe this source, actually, my dear students, let's do something very interesting, which is totally far from our semiconductors and solid-state electronics. Let's do it in a very different manner. Let's see. Okay, so let me now, okay, I'm sorry, let me turn my camera. Okay, perfect. Let's stop sharing for a while and let's do it. Okay, let's do a very easy example. You can make it with your younger sister or daughter. It's very easy like that. I'm sorry, younger sister or brother. So, okay. If you have two water tanks like this, like these two tanks, and you start, for example, the water level in tank number 2. This is tank number 2, this is tank number 1. So the water level in tank number 2 is up till this level. And you start to fill in water, drop water in tank number 1 till it reaches this level. And then you open the valve here, controlling these two or connecting these two tanks. What will happen, very easy, is that water will move from the higher tank to the lower tank. Very light, I think. So water will start to move from the higher tank to the lower tank till both tanks are on nearly the same level. This is an example. Okay. What is the second example? I don't know if you are from those who are interested in having tea. Maybe a lot of Egyptian like having tea, and this is an example of a tea process. I don't know if you used to make your teacup or not, but if not, please go to your kitchen and start now preparing a cup of tea. So what easily happen is as follows. This is a cup of tea. Then you drop the tea packet here, and then you drop the hot water. Okay, perfect. At t equals 0, the starting point, no tea particles are in the water. All the tea particles are here. Now let's start to think. Here is a very high density region. I mean, this is a region where you have a compressed particles of tea. And here is nearly very low density region. After a while, what will happen? Tea particles will start to what called diffuse here. This is what's called diffusion. So the tea particles will start to diffuse here, so that you will start to see that this clear water, this transparent water, will start to have this reddish and then this black color, depending on how much time you will keep the packet inside that hot water. So very simple, what's happened is the higher concentration, the higher density region diffuse to the lower concentration region. Here is the higher concentration region and here is the lower concentration region, which is I already demonstrated for you in this slide. If you can see that now my slides, as you can see here, you have a high concentration region and you have a low concentration region, and the tea starts to diffuse inside the lower concentration region. Okay, this is what about water and tea. But what about solid state electronics? Where is the electronics here? Okay. Let's make a very simple example in order to understand it. imagine the following. Let's use a relatively clean paper. Okay, please imagine the following. You have two pieces of semiconductors. Oh, one piece. I'm sorry. It's one piece of semiconductor. Let's say this is a silicon semiconductor, which has an intrinsic concentration of 10 power 10 centimeter per minus 3 at room temperature. And then you divide this piece into two regions, this region and this one, is the right-hand side and the left-hand side. In the left-hand side, in the right-hand side, we will keep this intrinsic. So you will not add any sort of doping or something like that. So what you are going to do is say that N here is equals to P is equals to Ni, which is simply 10 per 10. But on the left-hand side, you will start to insert some sort of doping. Let's say, for example, Nd is equal to 10 power 17 per meter per minute. So if you would like to write here the electron and the hole concentration, it's very simple. I believe you can do it in a very easy manner. You will say that N is approximately equal to Nd, which is equals to 10 power negative, or sorry, not negative, 10 power 17 centimeter per minus 3. And P is equals to Ni squared over N, which is equal to 10 power 20 over 10 power 17, which is equal to 10 power 3 centimeters. Okay, very perfect. Okay, now I will go to your exam, and so I told you, please, my dear student, please plot a relation between X, the dimension, and N, the electron concentration. Oh, very easy. In this region, N is equals to 10 power 10. And in this region, N is equals to 10 power 17. Again, you can see it. This is the high concentration region, and this is the low concentration region. The same example for the teacup or the two water tanks. This is the high concentration, this is the low concentration. Then you should expect that electrons will diffuse from the higher concentration region to the lower concentration region till you have what's called a uniform concentration. So whenever we have two regions with two different concentrations, either in the electron side or the hole side, we should expect what's called a diffusion current. Then this diffusion current is simply due to difference in concentration, due to variation in concentration. Whenever you have a variation in concentration, you have a diffusion current. Accordingly, we can say that we have two types of current. The first one is a drift current, which is due to the electrical field or the potential. And the second is due to the difference in concentration. Let's now return back to my slides. This is actually very, very important, my dear student. You have to recognize it very well because we will use it more than one time while dealing with different semiconductor devices. So, what about concentration? Or what about diffusion? Diffusion is the diffusion of the carriers from a higher concentration region to a lower concentration region till we reach what's called a uniform distribution or a uniform concentration. How we are going to make it, or how we are going to make such a device, or what is the condition to have such concentration. Here, this is what's called the non-uniform doping. What I mean by the non-uniform doping is simply what I did here. I make this is I doped this area, and I did not dope this area. So you have non-uniform doping. This area is only the doped area on the device or in the material, while the right-hand side area is not doped. So the concentration of the doping is not uniform. So One of the reasons to have a diffused current is to have a non-uniform doping, as you can see in my current slide. Okay, sorry. Herein, you can describe the variation of the carriers by this relation. Here is the high concentration carrier, and here is the low concentration carrier, and carriers start to diffuse from the higher concentration region to the lower concentration region. Very important. Okay, now we can understand the concept. We have now the concept, the physical concept of the diffusion. But how we can demonstrate such a concept mathematically? In the first model, where we are dealing with the drift current, our mathematical model depends on eta, which is the electrical field. Here, what is the main factor depending on our mathematical model is? What is the factor at which we can depend on our mathematical factor? So, in order to answer this question, let's make it very easy. So, okay, so very simple. As I told you, the key factor is the non-uniform concentration. So if you are going to plot x versus n, if the function looks like this, and I told you, do you have a diffuse current in this relation? You will tell me absolutely no. There is no variation in concentration. So whenever you have this solid straight line, it indicates that no diffusion current. Because simply all the device, all the material has the same concentration. But what if the concentration looks like that? Here you will tell me, okay, here we have a diffusion current, because here this is a high concentration area, and this is a low concentration area. So electrons will drift, or I'm sorry, it will not drift. Electrons will diffuse from here to there. So what is the difference between, let me say this is N1, and let me call this N2. What is the mathematical difference between this N1 and N2? This is simply what we call differentiation. As you can see, dN1 by dx is equals to 0, because N1 is a straight line, it's a constant. So the differentiation of any constant is equals to 0. But dN2 by dx exists. Then we can model, this is the conclusion, we can model the diffusion current in form of the variation with respect to x, with either the n, which is electrons, or the p, which is hole. So the sign of having a diffusion current is to have a different concentrations, which can be modeled mathematically by the term d by dx. Let's now return back to the presentation. So again, by going here to the presentation, you can say that the diffusion current due to the electrons, if you remember in the drift current, we already split it into Jn and Jp. Again, we will do the same. Here, this is the diffusion current due to the electron is equals or is proportional to dN by dx. And the diffusion current due to hole is proportional to dP by dx. Here, dN and dP, d capital and d capital P are called the diffusion coefficients, which indicates the rate of diffusion. Maybe we will talk about it in more details few seconds later. And the Q, of course, is representing the charge. But you can recognize that I'm using a negative sign in both in N and B. So this negative sign is not due to electron, because we are using it even in the whole part. So it's not due to electron. It's a generic negative port. So why we are using this negative port? This is a very important question. Actually, we are using this negative sign very simply because your motion is from the higher concentration to the lower concentration. So this curve will usually be with a negative slope, as you can see, because it's simply dp by dx and dn by dx for this line or this reddish line is a slope. And as you can see, usually or your motion will be all the time from the high concentration to the lower concentration. So in all cases, you will have this line with this negative slope. Accordingly, you can insert this negative line all over the path. Now you can add another negative here to represent the charge due to electrons. So this negative will be turned into positive due to the electron charge. However, this negative will be kept negative. This is the model at which we can describe what's called the diffusion current. Now we can write this important, very, very important equation, what's called the drift diffusion current. As you can see here, you have 4 components of currents. The first one is what we call the drift current due to electrons. From where I have recognized, first, whenever you find an eta, then this is a drift current. And as you can see, this is N, this is electrons. Then this is a drift current due to electrons. Then, with a positive sign, we have the diffusion current, because we have this dN by dx, again due to electrons. If you remember, this positive sign comes from negative, negative, positive. So we have this positive sign. Then you have the drift current due to holes. It's a drift because it's eta, and it's holes due to this P. And finally, with a negative sign, you have the diffusion current due to holes. So this is the most important equation to describe any electronic device. Transistor, MOSFET or VGT, tunneling field effect transistor, thin film effect transistor. We also can p-n junction diode. Whatever you are doing as an electronic device, you can use this drift diffusion model. However, here we have to mention a very important note to those students who are interested in electronics and they are willing to complete their life dealing with electronic devices and modeling. This equation is under the umbrella of what's called the semi-classical model. What is the semi-classical model? If you take care, we usually describe electrons as it is a particle which is moving with a velocity called the drift velocity and has a mass and all this stuff. So whenever you are dealing with an electron as a simple particle moving in space using Newton mechanics, we call this what's called a classical model. So the classical model is a model where you are dealing with electron as a normal particle in space. But this is a semi-classical model because in some portion of this model, in some parts of these models, we use the quantum model. If you remember, my dear students, when we define the effective mass, I told you, please don't ask me where this EK diagram comes from, because this EK diagram comes from quantum mechanics. When we define the energy of states, the G of E, GC of E, and GB of E, I told you, oh, don't ask me this from where this comes. This is a quantum output. So from time to time, we use some limited quantum outputs. That's why we call it a semi-classical. Originally, it's a classical. We are dealing with electron as a particle, which is moving with a certain velocity. However, in some cases, especially in the effective mass, we introduce some very simple quantum models. Fortunately, you can use this equation to model devices whenever the dimension of these devices is relatively large. I would say greater than 1 micrometer. However, whenever your device is in the sub-micrometer range. Whenever you are going to do these new transistors dealing with the sub-nanometer, in the 10 nanometer and 7 nanometer and 14 nanometer range, you will not be able to use this equation in order to model the your device, and you have to turn to what's called the quantum mechanics model, where you are going to investigate more about these devices. Actually, this quantum mechanics model for our curriculums is considered as a postgraduate topic. You will not hear about it again in any course. Maybe in your future, if you are willing to prepare your masters in electronics, then or semiconductor devices, then you may hear about this quantum model. Now, this is a general equation for the drift diffusion current. It's called the drift diffusion simply because your current is either due to drift or diffusion, due to electrical field or due to variation in concentration. One more slide remaining in this lecture, which is for me one of the most interesting slides. When I start to describe this drift and diffusion model, I used to say what is the reason for the current. For example, when I start to describe my drift model, I told you that this is simply due to the electrical field. And when I described to you the diffusion current, I told you that this is simply due to the variation in concentration. So from a first impression, you can see that both are totally different. The reason of having these two currents are totally different. One is due to the potential, one is due to the potential source or the electrical field, and the other due to the variation in concentration. So basically, you can say that, okay, these two sources of current are totally independent. However, one genius guy, maybe 100 years ago, which is Einstein, have proven that both types of currents are correlated, are hardly correlated. Simply, by correlating these important two parameters, the mu n, or the mobility of the electron, with the dn, or the diffusion coefficient, and the mu p, which is the mobility of holes, with dp, which is the diffusion coefficient of holes, by this equation. dn over mu n equals kt over q. dp over mu p equals kt over q. By the way, this term kt over q is a very interesting term in our electronics. I have to mention it here. The term kt over q, of course, k is a constant, which is Boltzmann constant. Q is a constant, which is 1.6 times 10 power negative 3. 1.6 times 10 power negative 19. At room temperature, this number will tend to 25.9 milli electron volt. We call it the thermal voltage. Of course, whenever the temperature changes, this number will change, but this is somehow a very famous constant. Usually we are dealing with semiconductors at room temperature, so we are usually using this number in this form. So what Einstein said that dn over mu n equals Tb over mu p equals this constant, kt over q. That means simply that Zn is directly proportional to mu n. Very interesting. And dp is directly proportional to mu p, and the constant for this proportional is kt over q. Another very important, interesting point, that dn is proportional to the temperature. If you turn it here, dn is equal to kt over q times mu n. dn is proportional to the temperature. Okay, what is interesting is here. What is interesting in the fact that the dn is, or the diffusion coefficient is proportional to the temperature? What is interesting here? Actually, yeah, it's not so interesting, but maybe you have to recall your cup of tea example. What is dn and dp? dn and dp are the diffusion coefficient. It indicates the diffusion rate. So whenever you have a higher temperature medium, your diffusion will be faster. That's why we are preparing tea in a hot water. because at hot water, tea particles will diffuse faster. Please try to make it in your kitchen. Go to your kitchen, pick up 2 cups, drop hot water in one, and drop cold water in another. Insert 2 tea packets and start to open your stopwatch and make a photo using your mobile. And try to make the 2 photos instantaneously. So you can start to detect the diffusion rate in both cups simultaneously. You will find that the cup where there is a hot water becomes reddish and black faster than the cup with the cold water. This is simply because the diffusion coefficient, or Dn, is function in temperature. So we have to thank to Einstein that he told us that we have to prepare tea with hot water because of this temperature. This is the end, my dear students. Actually, this is the end not only for this lecture. This is the end of the first part of this course, where we were dealing with what's called the semiconductor fundamentals and material. We start with the first principle, chemistry and physics theory, where we have an isolated atom and an energy band. And we go together in a journey where we have studied what's called the intrinsic semiconductor material, the extrinsic semiconductor material, and we also study the energy band diagram, and finally we study the concept of current motion, either due to drift or diffusion, and finally we combine this in one equation named the drift diffusion model. This is the end of the first part of our module. Starting from the next lecture, my dear students, we will go into devices, starting from the diode, metal oxide field effect transistor, metal oxide semiconductor field effect transistor, or what's called MOSFET, bipolar junction transistor, and finally the thin film transistor, or the TFET. This is our journey. Hope that you are enjoying our course up till now, and see you in lecture number 4 under the title PN junction. Thank you very much.